Hi. So in this video, we will derive the stiffness matrix for one-dimensional linear bar element. So what we know from the previous, what we know from the previous lecture is, so this is the bar element, say node one and node two, and n one and n2 are the shape functions, where n1 is equal to L minus h by L, and n2 is equal to n2 is equal to h by L. Okay. So now we will go and derive the stiffness matrix. So the general formula for the stiffness matrix is, so I am going to write the general formula. See the general formula for stiffness matrix. Okay. So it is going to be the stiffness matrix is represented by K. So K is equal to integral over the volume P transpose D P into dV. So this is the general form of writing a stiffness matrix. Okay. So K is the stiffness. So K is the stiffness. Okay. And this is the D is the elasticity matrix. Elasticity matrix. So K is the stiffness matrix. So it should be in the matrix form. And B is the it is the derivative of shape function. It is the derivative of shape function. It is the derivative of shape function. Okay. So let us try to derive the stiffness matrix for one dimensional linear bar element. Okay. So from the generalized form, we need to rewrite this stiffness matrix for one dimensional form. Okay. That is, so the integral, it is with respect to the v, that is a volume integral. There is a volume integral here. So we have to convert this one into a line integral, because in one dimensional linear bar element we are dealing only with one axis system, that is the x-axis, which is from 0 to L. Okay. So I have to change the integral. So how we can do is, we can rewrite this k, the stiffness matrix k, as integral 0 to L b transpose d b. So instead of v, the volume, I'm going to write it as the area into dx. Okay. So I have converted the volume integral into a line integral. So that is what we have done. Okay. Fine. So so what is our aim is to so what we need to do is, we need to find each and every term of this and multiply it, integrate, and get the value of the stiffness matrix K. That's all. Okay. So it is only simple substitution. Fine. So let us try to do it. So for one dimensional problem, for one dimensional bar member, the the elasticity matrix, it is equal to the Young's modulus. It is y is E is the Young's modulus. So what is the meaning is, instead of, there is no need for me to find the go and calculate D. D is nothing but it is equal to the Young's modulus E here for one dimensional problem. This is applicable only for one dimensional bar. One dimensional bar only. It is not for beam or any other element. It is only for the bar. One dimensional bar. My elasticity matrix D is equal to the Young's modulus of the material E. So then we need to go and find what is B. So to find B, what is B is, B is nothing but the derivative of the shape function. So what is the shape function? Uh, I have to derive. I have to take the derivative of it. So the shape function is say n1 and n2. I can write this. I can write it in the matrix form. The shape function. So what should I do? I have to take the derivative of this. So d by dx of n1 and n2. Okay. So I have d by dx of what is n1? N1 is L minus h by L. Okay, and n2 is h by L. Fine. So if we take the derivative of this, we have, so if we take the derivative of L minus h by L, we will be having minus 1 by L, and if we take the derivative of h by L, we have 1 by L. Okay, so that is B. So if B is minus 1 by L and 1 by L, it is a row matrix. What will be B transpose? B transpose will be the, it will be, we have to just take the row into column and column into row. So minus 1 by L and 1 by L. This will be the B matrix. Okay. So now we have found all the values, all the terms which is present inside the K. So what we know what is B transpose, we know what is D, and we know what is B also. So A is the area of cross section, and we have to just integrate it. Okay. So let us try to multiply everything and get a standard form of writing this stiffness matrix for a one-dimensional linear bar element. So we have K is equal to integral 0 to L B transpose. B transpose is minus 1 by L and 1 by L. B transpose multiplied by the Young's modulus E and the row matrix minus 1 by L and 1 by L, that is the B, into A into dx. So this is what we have. So let us take the let us keep only the x variables inside and we will take the other terms outside. So we have A, E, even the terms which are present inside the matrix also are also, it is like a constant term only. It doesn't depend on x. So I can take that one also outside. So AE into, we have minus 1 by L and 1 by L multiplied by a row matrix that is minus 1 by L and 1 by L. So I have taken the terms just outside the integral 0 to L into dx. Okay, so if you multiply AE, so this one, it is a 2 cross 1 matrix and it is a 1 cross 2 matrix. So if we multiply, we will get a 2 cross 2 matrix. So that is what we will get. So the first term will be 1 by L square. The second term will be minus 1 by L square. The third term will be minus 1 by L square, and the fourth will be 1 by L square. Okay, multiplied by, so integral of dx, it is x from 0 to L. Fine. So now I can write this one as AE into, I can take the L square outside by L square 1 minus 1 and 1 multiplied by, we have h is equal to L. So finally we have K is equal to AE by L into 1 minus 1 and 1. So this one, it is the stiffness matrix for one dimensional linear bar element. Okay, so this is the stiffness matrix for one dimensional linear bar element. Okay, so in the next video we will discuss about the quadratic bar elements and try to derive the shape function and stiffness matrix for a quadratic bar element. Okay, thank you.